So hello everyone. We're back with the quotient rule, continuation of last day's product rule. So it's going to go ahead and introduce the quotient rule as is. It says here if you have a function y equals f of x over g of x, where f of x and g of x are function respectively, and then the derivative y prime would be equal to f prime of x g of x minus f of x g prime of x. And then you'll all be divided by g of x squared. Oops. Okay, like so. So there is a nice mnemonic device that people use, low, d high. So low as in g of x, and then d high as in the derivative of the f of x. So this is g of x, and then f prime of x minus, then of course, f of x, and then the derivative of the denominator, which is of course g prime of x. And this will be all over, as you may have guessed, low squared. Right, so that would be g of x all squared. So what we're going to do is we're going to go over a couple of questions where we use the quotient rule, and then there will be a couple of questions where we um, show you why we don't have to use the quotient rule. Okay, so now before we go ahead and do that, there are some special cases. So for example, let's say you have a function here that is y equals to c over g of x. Now, of course, g of x is a function in terms of x where c is a constant. So let's see what happens if we have a constant divided by a function. Well, there's two ways of looking at it. You can think about it as c and then g of x to the -1 power. And then you can apply what is called the chain rule. But we will not be doing that until later on this chapter. So instead, what we're going to do is simply take the derivative using the quotient rule and see what happens. Now, as you know, the derivative of a constant is 0. So we have 0 multiplied by g of x minus, and then c times g prime of x. And then this will be all over, as you know, g of x squared. Now, of course, you can simplify this, and you will simply be left with negative c g prime of x all over g of x all squared. And we will use this formula for one of the examples later on. Sorry about that. Let's go ahead and fix it. We were left with g of x all squared. And then the result is negative c g prime of x all over g of x squared. Okay, so let's look at some questions where we basically have to use the quotient rule. Starting with example A, p of t is equal to 3t plus 9 all over 2 minus t. So let's look at what we get if we apply the quotient rule. So we will take the derivative of the 3t plus 9, which of course is just 3. And then the denominator is 2 minus t. And then minus 3t plus 9, and then the derivative of 2 minus t is just negative 1. And this will be all over 2 minus t squared. Okay, so from there, we can multiply things out a little bit and try to simplify this as best we can. So we have 6 minus 3t, and then minus negative 3t minus 9, all over 2 minus t squared. So if you're not sure where the negative signs are coming from, we simply distributed the negative 1 through um, the set of parentheses that's around 3t plus 9. Keep on expanding here. So we have 6 minus 3t plus 3t plus 9. You notice that in this particular example, the 3t's will eliminate each other, so that's good. And so in this case, we'll be simply left with 15 over 2 minus t all squared. And that is as much simplifying as you need to do for this kind of question. And so that's all you need to do. You don't need to expand the 2 minus t squared and multiply that out. That's not necessary. So for the next example, now we have a square root of x in the numerator for square root of x over x squared minus 2. So the first thing you want to do is probably just rewrite this a little bit. We're going to rewrite this as 4x to the 1/2 power, and then all over x squared minus 2. Of course, there's no simplifying there. Oops, sorry. All right, so if we take the derivative, again, using the quotient rule, we'll take the derivative of the 4x to the 1/2, which of course is 2x to the negative 1/2. And then the denominator is just x squared minus 2 minus 4x to the 1/2. You leave the numerator as is. And then the derivative of the denominator is 2x. And this will be all over x squared minus 2 all squared. So now we will apply the distributive property. We have 2x to the 1/2 power. Oh, sorry, not 1/2. 2 minus 1/2 is 3 over 2. And then 2 times 2 is 4. X to the negative 1/2. And then minus 8. And once again, this will be 1/2 plus 1 would be 3/2. So you can see in this case, we do have some like terms we can combine. And then here we have x squared minus 2 all squared. Of course, that doesn't change. You don't have to expand it, just like in the previous example. So now if we combine like terms, we have negative 6x to the 3 over 2 minus 4x to the negative 1/2 power all over x squared minus 2 all squared. So last thing you have to do is to rewrite the powers of x. Now, of course, x to the 3 over 2 can be rewritten as x root x, or the square root of x cubed. Either one is okay. You can choose. I prefer x root x. So x root x, sorry. Minus, and this is of course 4 over the square root of x, and then all over x squared minus 2 all squared. So these are a couple of examples where you can't really get away from not using the quotient rule. Okay, So one of the things we can do in this chapter is I can give you questions that look like you have to use the quotient rule, but you actually don't. There's usually something clever you can do in that kind of question. So if you look at example C, y is equal to 4 over x squared, we can use the corollary that we just made up. So that is this right here. We can apply that to take the derivative without doing too much work. That's one way of doing it. So let's see what we have. Another way of doing this question is to rewrite um, y equals 4 over x squared as y equals 4 and then x to the negative 2 power. Then, of course, we can use the power rule to take the derivative. We have negative 8x to the negative 3 power, or quite simply negative 8 over x cubed. Now, if you use the corollary of the quotient rule from above, you can actually get the derivative. Oh, sorry, this is a derivative. The derivative to be, again, negative cg prime of x all over g of x squared. And we know that corollary will work here because 4, of course, is a constant. So it will work. So let's look at the derivative then. This will be negative 4, and then the derivative of x squared is 2x. And then in the denominator, we'll have, well, x squared squared. So the derivative in this case will be equal to negative 8x all over x to the 4th power. And of course, that is the same as what we had earlier, and that is negative 8 all over x cubed. Oops, sorry. Didn't mean to do that. Again, all over x cubed. Okay, so now the question, example D, again, we don't have to use the quotient rule, although we do have a quotient, because what you can do is rewrite z of w as 2w to the 6th power all over 4w cubed minus 3w squared all over 4w cubed. And then if you simplify the terms, you have 1/2 w cubed minus 3/4. And then you can write it as probably w to the negative 1 power would be easier. And then you can take the derivative using just the power and constant rules. So z prime of w is equal to 3/2 w squared, and then plus 3/4 w to the negative 2 power. Just straightforward application of the power rule, right? So the 3, and then this 3 becomes a 2. That's how you get 3/2 w squared for the first term. And then the negative 1, of course, goes to the front, becomes a plus here. And then the negative 1 becomes a negative 2 power. So all you're left with is to rewrite this slightly. So you have 3 over 2 w squared plus 3 over 4w squared, where the w squared in the second term is in the denominator. So you don't write it with a negative exponent, but a positive one. So the last little bit about the quotient rule is kind of combining what we learned so far with some application question here. So it says, suppose the volume of air in a balloon at t seconds is given by the formula. V of t, so volume in terms of time, is equal to 6 times the square root of t divided by 4t plus 1. So we're going to see if the balloon is being filled with air or losing air at t equals 8. So the thing that you must recall is that if the derivative is positive, then the volume is increasing, which means it is being filled with air. If the derivative is negative, then of course the volume is decreasing and it is losing air. So in this case, we will rewrite the square root as a power of t, t to the 1/2 power. And then we can apply the quotient rule. So v prime of t is equal to, let's see, um, so low, so 4t plus 1, d high, so derivative of the numerator is 3, and then t to the negative 1/2, and then minus high, so it would be 6t to 1/2 power d low, which is 4, and then it's all over 4t plus 1 squared. So in this case, we will not expand this because all we need to do is substitute 8 directly into the derivative to find out whether the balloon is being filled with air or losing air at t equals 8 seconds. So that will be 4 times 8 plus 1, and then 3 times 8 to the negative 1/2 power minus 6 times 8 to the 1/2 power times 4. And this will be all over 4 times 8 plus 1 all squared. So 4 times 8 plus 1 all squared. And if you evaluated this, you actually get a negative number, a very small negative number, but it is negative nonetheless. I'll leave you to evaluate it using a calculator. And then this is, of course, losing air. Okay, so that is the quotient rule. We managed to talk about the quotient rule itself. We applied it. We look at some questions that look like they might require the quotient rule, but it turns out they don't. So that's example C and D. There are other ways to do questions and find derivatives without using the quotient rule, even though there are quotients involved. And then we did a quick application question at the end. So that's it for today. Thank you for listening.